Hey there, and welcome back to the channel. This week we're going to be talking about the 8 core technologies needed to land a reusable rocket back on land or on a barge in the ocean. So let's give you all a crash course. What? We don't use the C word? Why not? For the past 2 decades, rocket stages have always been thrown away. But all of that changed in December 2015 when SpaceX finally landed their Falcon-9 first stage back on land. And since then, they've made 150 or so landings successfully, both on land and in the ocean. That's a huge achievement. They made 161 attempts and 150 successful first stage landings. That's a 93% success rate. So let's figure out what technologies SpaceX and other competitors will use to land rockets back on land and in the ocean so we may reuse them and reduce the cost of spaceflight way down so we can democratize access to space. The first is a pyrotechnic ignition system. A rocket engine ignition system is some sort of pyrotechnic device that generates sufficient thermal energy in the form of, say, a flame to relight the rocket engine as it slows down when it enters the Earth's atmosphere or when it's back landing at the landing pad or out in the ocean. So for a rocket booster to successfully land back on land, the booster needs to relight itself reliably at hypersonic velocities in the upper atmosphere and supersonic and transonic velocities in the lower atmosphere, as well as the low subsonic near zero velocity when the rocket booster is about to land back on land or in the ocean. Let's talk about booster attitude control. Attitude control for a rocket is the process of controlling the orientation of the rocket as it ascends and descends through the upper atmosphere. On expendable boosters, attitude control is typically achieved by means of engine gimbaling, but newer technologies are needed to enable booster attitude control to enable it to land back on land or in the ocean. This is key because we need to ensure the booster maintains correct orientation through multiple phases of reentry, the 4 phases of reentry being the boost back phase, the reentry phase, the terminal guidance phase, and the landing phase. The orientation of the booster must be such that it has a non-destructive entry profile upon entering the Earth's atmosphere, but it must also generate sufficient aerodynamic control authority to enable precision landing. Moreover, the roll rate of the booster must not overwhelm the entire system because if it rolls too much, the fuel in the fuel tanks could centrifuge or slosh out and it could shut down one of the engines, resulting in a failed landing. In addition to the booster attitude control system itself, supporting technologies such as the grid fins must be capable of handling transitions from hypersonic to supersonic velocities, as well as handle the stresses of engine firing. Speaking of grid fins, let's talk about grid fins. They're an unconventional type of control system that you've probably seen on the Falcon-9. On most rockets, you've probably already seen a version of grid fins being used, and they're the planar control fins. While planar control fins act as miniature wings, grid fins act as a large lattice of aerodynamic control surfaces, but in a much smaller volume. The main challenge with planar control fins on rockets is that it becomes very hard to turn them when there are large aerodynamic forces at play. I mean, imagine trying to open a door when on a calm day versus a day when there's a hurricane blowing through it. This is where the advantage of grid fins come into play. Grid fins allow for an increase in precision while reducing the amount of torque needed to actuate them. Because of their lattice structure and their crisscross nature, it's much easier to actuate them in a high-speed flow. They don't require as much torque. And thanks to their relatively small shape, they can easily be folded up against the rocket body, and you can see them stow aerodynamically against the rocket during launch and deployed with relative ease. However, grid fins aren't always fantastic. Engineering a rocket is always a complex trade study and involves tons of compromises, so their effectiveness isn't great throughout the entire range of flight. Because of the formation of a normal shock wave, the drag on a grid fins can increase appreciably at high subsonic or supersonic speeds. The flow characteristics do improve, however, as you pass on either end of this speed range. It's just in that subsonic, high subsonic to low supersonic range where the normal shock wave exists that deteriorates the characteristics of the fins. Otherwise, it's great. By the way, contrary to popular belief, grid fins were not invented by SpaceX. They were instead invented by a Soviet ballistic missile designer named Sergei Belotserkovsky in 1956. Let's talk about throttling a rocket engine. Throttling a rocket engine is similar to the process of throttling a car, where the rate of combustion of propellants, the fuel and oxidizer, is controlled. This in turn controls the amount of thrust, or the total upward force that the rocket engine produces. Typically, a rocket can only be throttled down to an exit pressure that is 1/3 of the local ambient pressure and up to a maximum limit as determined by the structural capabilities of the rocket engine itself. Deep throttling is a key technology to successfully design into your engine because a landed booster needs to be able to achieve zero velocity at precisely zero altitude. So say it with me, zero velocity at precisely zero altitude. If the booster achieves zero velocity too late, it simply crashes, and if it reaches zero velocity too early, it just starts going back up. At that point, cutting your engines and falling back down is the only option and results in the same crash. Plus, the degree to which a rocket engine can be throttled down greatly varies. The typical limit is combustion stability, as the injectors need a certain minimum pressure to avoid damaging oscillations, also called chugging. Nope, not that chugging. SpaceX's Falcon-9 and Starship, as well as Blue Origin's New Sheppard vehicle, have successfully achieved this key criteria of zero velocity at zero altitude. So this is part 1 of the video, and we covered how to reliably restart a rocket, how to maintain the correct attitude and orientation in the rocket using booster attitude control systems and grid fins, and we talked about how deep throttling a rocket engine is important to be able to precisely achieve zero velocity at zero altitude. Stay tuned for part 2.